Hello, in this video we're going to talk about linear regression. It goes along with section 10.2 in your text and also with the correlation and regression notes that can be found on Blackboard. In this section we're going to learn how to make a regression line in our calculator. It's also known as a line of best fit or least squares line. The least squares part comes from a formula that you can use in order to come up with this line, but we're going to use our calculator skills. So a regression line is given a collection of paired sample data, that means ordered pairs, x, comma, y. The regression line is a straight line that best fits the scatter plot of the data, so then we can use it to approximate. The regression equation, we have y hat equals b naught or b sub 0 plus b sub 1 x. That describes the regression line. The regression equation expresses a relationship between x, which is your explanatory variable, or also called your predictor variable or independent variable, and y hat, which is called the response variable or the dependent variable. So you should see that this looks very much like your linear equation of the form y equals mx plus b, only we have our versions switched here. So what we have here is this b naught would be like our y-intercept, and the b sub 1 would represent our slope in the equation. And once again, we're going to use our calculators to come up with these equations. You can see in this table here, we have just some of the notation that we use in statistics class. The y-intercept of a regression equation I just told you is b naught, and that's talking about sample data. If we were talking about population parameter, we have the capital Greek letter for b. So the only difference here you see on the left and the right is that for sample statistics, when we're coming up with our equation for our line, we have lowercase letters, and we have y hat as an approximation. This triangle on top is called y hat. But then for the population itself, we have capital letters here, and we can use y because it's not an estimate at that point. We're going to learn how to find the equation of a regression line in this section, but first we need to know the requirements. First off, you need to have sample data, XY data, and it should be a random sample of quantitative, which means numeric data. So what you're going to do is you're going to plot that data and take a visual examination of the scatter plot. And you're going to see, did they look like it should go with a straight line pattern or not? So that's just through visual examinations. Plot it and take a look. Also, you want to take a look at outliers because outliers can have a strong effect on your regression equation. So you might want to remove any outliers if they're known to be errors. Consider the effects of any outliers that are not known errors. These are all things to consider. So requirements 2 and 3 are kind of simplified attempts at checking these formal requirements for regression analysis. So for each fixed value of x, the corresponding values of y have a normal distribution. For different fixed values of x, the distributions of the corresponding y values have the same standard deviation. This isn't true if part of the scatter plot shows points very close to the regression line while others are more scattered away. And for different fixed values of x, the distribution of the corresponding y values have means that lie along the same straight line. Once again, when we do our visual examination and we check for outliers, we're meeting those requirements. Once we make a regression model for a set of data, we can use it to make predictions. So regression equations can be useful in predicting the value of one variable given some specific value of another variable. But first we have to consider whether we have a bad model or a good model. We consider a model to be a bad model if the equation does not appear to be useful for making predictions. So don't use the regression equation for making predictions in that case. For bad models, it's best to predict the value of the variable is simply the same as the mean. So that would be the mean of the y values in your data set. For a good model, you can go ahead and plug in the given x they want you to predict for into your equation to get out your y hat value. So use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. On page 4 of your guided notes, you can see this flowchart that helps you to figure out whether you have a good model or a bad model and what strategy you should use for predicting your values of y. Let's look at an example and we'll use our calculators to find the equation of a regression line in which the explanatory variable is the chocolate consumption in kilograms per capita and the response variable or Y variable is the corresponding Nobel laureate rate in particular countries. So we have a list here. It's actually split in two, but our X values are represented chocolate consumption per capita in particular countries, and the Y values are the Nobel laureate rates. So here we would see we have the point 3.7, 5.5, and so forth. We're going to put these in our calculator. Now, if you scroll back to page 3 of your guided notes, all of the directions that I'm going to go through right now are right there for your reference, and they're also in your calculator steps document, but I'm going to go through all of these steps starting now, so have your calculator out. Before we even put anything into our calculator in this section, you'll notice that it says before starting on chapter 10, materials, we want to turn our diagnostics on our calculator. So we're going to follow those instructions. Press second, and then 0 to get to the catalog. When you're at the catalog, you're going to scroll down until we get to Diagnostics on. And we'll keep scrolling until we get there. And then you're going to press Enter. And then Diagnostics on will show up on your screen. Press Enter again and it will say Done. This is going to allow us to see all of the things that we need to see when we find our regression line. We'll be able to find R and all of the things we need to see this way. Now, I'm going to scroll back to our example, but we'll take a glance here. We're going to learn how to draw a scatter plot. We're going to put data into our list 1 and our list 2, and then we'll draw our scatter plot. That's the first thing that it says here. And then we're going to find our correlation coefficient R, and we're going to plot our regression line. So the directions are here, but you can follow along with me on the next page as I go through it with you. For our data set, we're going to go to Stat and press Edit. And in list 1, I want you to put all of the X values that you see, so all of the chocolate values in order from the first set and the second set. All of those go into list 1. So what you do is you type in the number. So we have 3.7, enter. Then the next number, 1.8, enter. It's important that you do it in the same order that we see here. So do that and we'll check back. Once you have all of your X values in, go over to list 2, and you are going to put all of your Y values in list 2. You want to make sure that you use the same order, starting at the top, because remember, 3.7 and 5.5 go together as an ordered pair, so they should be next to each other in the list. Right here, 0.7 and 0.1 go together as an ordered pair, so they should be next to each other in your list 1 and list 2. So go ahead, pause the video, and get all your Y values in order on list 2. Once you have all your data values in list 1 and list 2 for your X's and Y's, it is worth going through and making sure that you have them in order, you're not missing anything, and you have no typos, because otherwise we're going to get different answers than each other. Let's take a look at our scatter plot of our data. So we're going to go second up to stat plot, and we're going to turn our stat plot 1 on. So highlight it and press enter if it's not on already. Now scroll down to type, and this time we're going to do the one that has the dots, because that's a scatter plot. It's the first one, so press enter on it, and then you simply need to press zoom and 9. And you can see here a scatter plot of our data, and it does appear to look like it might be linear. As X increases, Y is increasing. If you have another line going through your data right here, what you should do is go to Y equals and just make sure all of these are cleared, because you probably have a line being plotted there if you have something else going through your graph. But that does look linear. Let's go ahead and find the equation of our regression line, and we'll find our correlation coefficient, and we'll view that line also. So let's go to Stat. Now go over to Calc, and we're going to scroll down to number 8, or you can just press the number 8 where it says ln reg a plus bx. So list 1 is where we put our x's, so we're going to put list 1. If you don't have L1 there already, you press second and then the number 1. And then you have list 2, which is L2. If you're a person that doesn't have this menu in front of you, you definitely want to have your calculator document out. And what you'll do is instead of pressing down to go to the next one, you'll press a comma and then type in L2. We did not use frequencies, so you can leave that blank, but we do want to store our equation. This says store reg EQ. To store our equation, what we do is we press vars and then go over to the right to y vars and function, and you can pick a place to store it. I'm going to pick 1, which is y1. And I'll go ahead and I will calculate. You can see here we have our y equals a plus bx. A is negative 3.157. That's our y-intercept. And b is our slope, 2.474. We'll round that to. So let's go ahead and write in our answer. We can also see our correlation coefficient, R, is listed here as 0.9995. And we can round that to 3 decimal places and we'll get 0.800 when we round up. I'm also going to write down what we get for R squared right here because we'll use that later. And it is simply the number 0.7995 on squared. And we get 0.639. We're just going to save that for later on in our video. Now, when we calculated our regression line, we also stored it in our y equals. So if you press y equals, you'll see that equation stored there. And when we press graph, we can see the line going through our scatter plot. We're asked using a 0.05 significance level is the regression equation a good model and why. If you remember on page 2 of this document, we have our Pearson correlation chart and we also have our rules for this. So let's look at page 2. We're going to look in our Pearson table that's going to be to the right of these notes, and if the absolute value of R is greater than our table value, we have a linear correlation, and if it's less than or equal to, we do not have sufficient evidence. So our absolute value of R is going to be 0.800. Let's compare it to the table. Our chocolate Nobel data had 23 items. We don't see the number 23 here, but we do have 25, which is close, and we were asked to use alpha's 0.05. So we're going to see where these meet, and they meet at 0.396. So let's go ahead and compare 0.396 with our 0.800. We can see that our R value is greater. Since it's greater, we can say we have a linear correlation. What does that mean? It means we can use this model for our data to make predictions. Going back to page 4, we're asked to predict the Nobel laureate rate if chocolate consumption for a country is 5. So that means x equals 5. And we can simply plug in 5 for x in our equation. And we get an answer of 9.213. While the model was a good fit, it seems a little bit suspect that there might be a relationship between chocolate consumption and a country and Nobel laureate. A couple of final vocabulary items to discuss. Marginal change. Marginal change is basically the slope. So it is how much does the y variable change when x changes by 1 unit. So for our Nobel laureate chocolate data, I've rewritten our equation here, but the slope of 2.474 tells us that if we increase the chocolate consumption by 1 kilogram per capita, the predicted Nobel laureate rate will increase by 2.474 per 10 million people. So for every 1 additional kilogram per capita increase in chocolate consumption, we expect Nobel laureate rate to increase by 2.474 per 10 million people. We've already talked a bit about outliers and influential points, but as you can see, 1 point can strongly affect your graph here. We can see with and without the 0.50 what happens to a graph. Finally, we have the coefficient of determination, which is R squared, and it's a proportion of variation in Y that's explained by the regression line. It's computed as R squared is explained variation over total variation. Now, some of your calculators will give you R squared, some will just give you R. Just simply square the number you get. So we have 0.8 squared to get our R squared for our chocolate problem. R squared equals 0.640 for the problem that we were doing. What does that mean? We can say 64% of the total variation in Y, our Nobel rate, can be explained by the linear correlation between chocolate consumption and Nobel rate, while 36% of the total variation in our Nobel rate cannot be explained by the linear correlation between chocolate consumption and Nobel rate. That 36% is explained by other factors. You can see a general model at the bottom.